So we want to discuss various types of quantum channels, okay? And then just we want to, which can be used as it is. So by a quantum channel, it is just a completely positive map, which is trace preserving. That's all. Or you can consider the dual channel, which is also a completely positive. I mean, it's equivalent to consider a dual channel, which is also a completely positive map, but it is unitary. These two are dual to each other. Okay. Okay. So we will consider on the state space, and both are same here, state space, and both are. I mean, if Mn, the star is again Mn. So on the state space, we will consider trace preserving map. On the covariant version is unitary. Okay. So the first very important thing is to preparation of the state. That is actually a quantum channel. You prepare it. How do you prepare? You just write it. That's all. I mean, in laboratory, it is not our problem. So first channel is, which is what is called preparation channel. What is a preparation channel? So you just have complex number C. Okay? It is just a map, rho P from preparation channel. So P, from C to L of HA. Okay? What it does is alpha going to alpha times rho A for fixed. Call it HA. Rho A in L of H. That's all. Okay. This is what is called the preparation channel. It's clearly a channel. We'll come to that. First, if you want to know, see whether it is a channel, this is just the, of course, it is trace preserving. A row of 1 will be, I mean, P of 1 will be row A itself. So it both will have, I mean, in complex number, trace is just it is as it is. It is just the identity map. So it will be, the trace of this is 1. No, trace of, I mean, row of, no, trace of alpha is alpha as a complex number. And trace of this is equal to, this is trace of rho is 1. So it is again alpha. So this is trace preserving. In the dual version, this is just the dual of just rho A itself. If we have rho A is a map from L of H. I mean, it's not a map from L of H. It is from L of H to C. Okay. But the map, this is not actually, this is, I mean, we have to consider phi rho A or something. Okay. But our map will be, which is just X going to trace of rho A X, right? Okay, rho A can be considered as a dual sitting in the dual. Okay. So I am just saying that this map preparation channel is nothing but the dual. There is just the star, whatever that, I mean, star of this rho A. So why it is true is the following. Rho A is from L of HA to C. Okay. Our P is from C to L of HA. Okay. The roles of the Hilbert spaces are reversed. And it should satisfy the following. Trace of, okay, trace of rho A with some trace of rho A with any alpha. I mean, rho A is not L of H from here. That phi rho A is L of H. I mean, let's see it by dual. I mean, you have to you can consider as linear functional, but after considering as linear function, it is basically the inner product kind of map, right? It is, there are inner product space. So it is a usual star, I'm just saying. So the star is the following. So you have this. So A is the alpha times Base of rho A T is equal to rho A. Yeah, that's what will give me the alpha. Base rho A T times beta alpha is equal to base of rho A times P of alpha. How do you write that? If you have, this is the map, right? To P star. Yeah. Okay. That's what I want to use. I want to show that this is just this map is just the star of this. Okay. So x or whatever be equal to alpha of can you just help me? Base of rho. And I want to write this equation just in Hilbert space form. But for that, P inside. Base of rho x times alpha is equal to yeah, is equal to P of alpha base of x right. Yeah, this is the image, right? This is for all x. P of alpha. This is the map P of alpha times x. Okay. This just implies P of alpha equal to alpha times rho. This is true for all x and all alpha. I mean, I just wrote the inner product in terms of this. Okay. I mean, the function T of xi, where xi is this x, okay, and this eta is in alpha, okay. Then the linear functional acting on x, the operator acting on this is T of rho x times alpha. So, which is equal to, this is that inner product. That inner product, you get P alpha, you get x here. So, this should be true for all alpha and x. So, this just means that P of alpha is alpha rho. This is just, I'm just showing that this is just the star of this rho A as a linear map. It's not needed, I'm just saying. I mean, we want to worry about Choi matrix, Krauss operators, and those things only, but just to understand. Okay. This is what is called preparation channel. Okay. The next channel is exactly same as preparation channel, but it is what is called appending channel. It is just, you have a, it is just appending channel. So maybe A, I don't know whether it is the right notation, A of any Y acting on B, okay, is equal to rho A times R Y. A is a map from HB, L of HB to L of HA tensor HB. When that HBC, it is just the preparation channel. Okay? It is just append something. Okay? These are all, you want to see that these are all completely positive maps. As I said, This trace is a completely, I mean, as I said, any state is a completely positive map. Okay, I have given you as a assignment, but you can see that a state, I mean, even if you have any finite dimensional, any positive map whose range is finite dimensional or even commutative, it will be completely positive. Okay, so the state is completely positive. I said this preparation channel is nothing but star of a state. State considered as a map, completely positive map, it's star of that. That is one way of seeing. Or there is another way of seeing these two as completely positive map. So let rho equal to, rho is a positive operator, so it will look like summation lambda I ei, right? Ei, ei. It will look like this, a spectral decomposition. Okay. Then you take ki equal to square root of lambda I ei, which is a map from C to whatever that space, HA. Okay. Right? This is a map. This is a map. This vector is a column vector. Is a column vector. So it's a map from C to there, right? C to there, no? A column vector, it will multiply C to there. Yeah. It's a column vector. So now Ki, any Ki, alpha, Ki star, okay, is exactly equal to that P of alpha. Okay. The summation. Summation. I mean, you will get an alpha in the middle. This star of that will flip, and there is an alpha in the middle, and it is precisely that. And this will get squared, and you get this. So these are the Krauss operator for this preparation channel. Similarly, so these are the Krauss operator for preparation channel. Krauss operator for the preparation channel. And similarly, you can take Ki to be so you have identity there. Ki to be square root of lambda I, Ei, tensor 1. Okay. This is a map from HB to HA, tensor HB. These are the Krauss map. So if you take summation Ki x Ki star, okay, that will give whatever the appendix channel. Okay. So this proves they are completely positive map. There's no duality. Dual map will be the Krauss operator will be become star of that. That will precisely you will get that. Okay. Okay. So these are so the assignment is, I will come to this. I will give some two, three more channel. The assignment is to compute the Chai matrix and the Stein-Spring representation, Stein-Spring isometric for this. Okay, it's very easy. I can orally say that also. You just have to prove it. Okay. So these things are completely positive map. Okay. And there is one more thing. We have to find that this is a channel. I mean, it preserves the state is clear. There also it preserves the state is clear. Directly you can verify. Or you can verify that summation Ki star Ki equal to 1, the identity operator. That also you can verify because it's summation lambda k should be equal to 1 because space of this is equal to 1. From that you can. If you take Ki star Ki star Ki will become Ei inner product is 1, and this will summation lambda A you will get that is equal to 1. Okay, so I hope I don't have to write. So it's clear. Okay, so it is traced. This is a quantum channel, preparation channel, appending channel, or quantum channels. Okay? Even though it looks trivial, there is some verification is needed. Then the next one is appending channel. There is something called replacement channel. If I miss something, I will recall it in the next class. I actually wrote the list in a paper, but I forgot to bring replacement channel. This is like some sort of rank 1 operator, but the rank 1 the corresponding one operator will be identity. Rank one in Hilbert space, you can define a rank one operator. If you have a xi, then you take the inner product of xi with some eta 1, and then you take eta 2. Okay, this will be a rank one operator. It's similar to that, except this inner product will be replaced by trace, and eta 1, eta 2, you will select them. Okay. The replacement operator is the following. Replace an R of any x, okay, or you can put rho if you want, okay, equal to trace of x times sigma. Sigma may be in B, this is in A. It replaces one operator xa by sigma b. Maybe you can call it rho A if you want, okay, by another state sigma b. Okay. Okay. And this is, of course, a state is, I mean, this is a preparation. I mean, this is just a composite. Taking trace is a channel. Okay. Trace is a positive, I mean, trace is a positive state. So trace is a channel. Okay. Trace, of course, preserves trace, its identity, and it is completely positive. And partial trace is also a completely positive. We have already seen. Okay. And so there is another replacement channel, which is R B or something. I mean, you can define a replacement channel as RXA to be. You take the if you take a rho A, rho RA in HR times R HA. Okay. Then you take R of rho RA is equal to take the A trace, partial trace with respect to A, rho RA. Then you replace with sigma B. Okay. So this R is from HR tensor HA to HR tensor HB. Okay. This is another replacement channel, but it works with tensor sigma. Yeah. No. Yeah. This will be just an R. This is in HR. This will be in HB. This is okay. And it is clearly the Krauss operator, it's clear. I mean, well, you will have a decomposition for this. Okay, and you have to compose those two things. So the assignment is to find the Krauss operator, Chai matrix, and sign spring for this. Okay. This is for replacement channel. Then there is something called trace channel, which we have just said. Partial trace channel, it just take the partial trace of one of them, and that's also a channel we know. Then there is, we have already seen isometry channel. We have already seen this, I'm just recalling, isometric channel. Isometric channel, if you have an isometry from HA to HB, then it is just isometry, I of x is equal to Vx V star. Okay. And it is already in the Krauss form. V is the Krauss operator. So this is already in the sign spring form, so you don't need to check all that. Okay. So if V is unitary, then it is called unitary channel. Then it is called unitary channel. Okay. And if V is unitary, if U is unitary, then the channel given by U star, that is x going to U star x U, is the inverse channel. It's all clear, I am just writing it. Inverse channel to x going to Ux U star. Okay. Now, if V is an isometry, then x going to V star x V is of course completely positive, because this is the Krauss operator for this, so it's of course completely positive. It is in that form. But it will not preserve the trace. For it to preserve the trace, we will need VV star. I mean, if you have something like Kx K star, then K star K should be 1. Okay, that is what the condition for trace preserving. This will preserve unit. This will preserve, this is unital. This will preserve the identity, but this will not preserve the trace. Okay, so we cannot have a inverse channel when it is isometric, but there is something called replacement channel, recovery channel, reverse channel. Sorry, reverse channel. Okay, there's something called reverse channel, which is like inverse channel, which will give a left inverse. Okay, so that's what I will describe here. So if you have a unitary, then the U star, the unitary channel given by U star will be the inverse channel. But if it is an isometry, then we have to do the following. Okay. So let B from HA to HB is isometry. Okay. Then, of course, X to Vx V star is isometric channel. It's a quantum channel. Okay. It's a quantum channel. That is, it is completely positive and it preserves the trace. Okay. Now you define R of Y, because it's from the other space, R of Y equal to V star X V, which will not preserve a trace. So we add the following: trace of, so this is from HA to HB, trace of 1 minus V star, okay, times X and times sigma for some sigma in sigma state, some state sigma on, it should be on HA, right? Where this R is from L of HB to L of HA. Okay. This X going to VXV star is from L of HA to L of HB. This is from L of HB to L of HA. And R, you call it as I of X equal to this. Okay. Then R of I will be identical. R is a quantum channel. And R will reverse the action of I. Okay. What happens is the following: I of X is Vx V star. You have applied an isometry, and you have got, this is actually, this will be a homomorphism also. I mean, if you have XY, then Vx V star, then Vx V star V will be identity. So it will be a homomorphism also. It will preserve the product. Okay. Then if, but you can't apply V star and get this V star XV, this will not preserve the state. So you add, this will reduce the state. So you add something. The reason is V star V is a projection. So if we take the trace of this, that will be trace of X V star V. V star V is a projection, strictly, if it is an isometry, strictly less than 1. So that will reduce the trace. Trace will be reduced. I mean, it will be less than the trace of X. Okay, traces are positive, so you can talk about it. So it will reduce the trace. So you add this. Okay. This is a V star V star is a projection. That is clear. I mean, because it's a partial isometry. For any partial measure, V star V is a projection, then V star is also a projection. Okay. So 1 minus V star is a projection. So we add this and we apply. That's a sigma I wrote somewhere, no? I erased it. There's a sigma here. Okay. There's a sigma. Sigma can be anything. It will work for any sigma because that will not play a role when you come. I mean, that will play a role. It will not play a role when you compose all these things. Okay. Proof of this. Okay. So what are the two things we have to verify? First, we have to verify it's a quantum channel. Okay. And that I think is clear because this is completely positive. This is completely positive. So the sum is completely positive. So this is completely positive. That's clear. For this to be completely positive, this is just, we have seen, it is just like a replacement channel. I mean, it's not like replacement channel because instead of 1, I have a projection here. 1 minus V star is a projection. V star is a projection. Of course, 1 minus V star is also a projection. So this is, but you can verify. Trace is nothing but like this, no? EI. 1 minus VV star. See, trace of VV star is just trace of V star X V, right? What I'm saying is, first you have this map. Trace of 1 minus V star X, okay, V star X is equal to 1, trace of 1 is 1 minus trace of V star XV. Okay. X going to V star XV is completely positive. Taking the trace is completely positive. Okay. And well, you don't need that. You take this as a projection. Let P equal to 1 minus V star. Okay. Then this trace of 1 minus V star X is equal to trace of Px. Okay. P is that projection. Okay. Because this P equal to P square, so you can take it that side. So trace of Pxp. So X going to Pxp is completely positive, and taking trace is completely positive. Then you are just appending to something which is completely positive. Okay. I mean, you are just attaching something that's completely positive. Sum of those two things is completely positive. So the whole thing is completely positive. There is no problem. But you find the cross operator and the other thing. Okay, you work on that. Let me see if it is difficult. We will do it in the class. Okay, I haven't checked. Okay. So this is the recovery channel. So this is completely positive. We have to verify that it's a quantum channel. We have to verify it preserves the trace. Okay, so trace of R of Y. Okay, trace of R of Y, which is trace of X V X V star V star, okay, plus trace of, I mean, this is just a number. Okay, trace of this is just a number here. Trace of this, instantly trace will come out, trace of sigma is 1. So you will only have this. Sigma doesn't play a role when you compute the trace. Okay, trace of 1 minus V star X. Okay, now trace of, I mean, this V star you can take it here. So trace of X V star, X V star will cancel. Trace of 1 is 1, this is 1. Okay, this is clear, right? This trace and this is same. V star, you can take it that side if you want, wherever you want. So this is, wait, trace of, no, you want to get trace of X, sorry. Yeah, this will be X, sorry, these two will cancel. 1 times X is X, not trace of 1, trace of, this is equal to trace of X. That's what we want. We want it to be trace preserving, not unitary. So trace of X. Okay. So it preserves the trace. Now we want to see that whether it actually reverses. So R of I of X, okay, that is equal to R of Vx star. Okay, we want to apply R of Vx star, and that is equal to V star of Vx star of V plus trace of 1 minus V star Vx star of sigma. Okay. Now V star V is 1, V star V is 1, so we get X here. So we have to get 0 here. So we will get 0, right? So we only have to get 0 here, which is trace of sigma, let it be. So we have to verify here, which is going to be trace of Vx V star. Okay. Now Vx V star V is 1 minus Vx V star, which is equal to, which is, it becomes 0. Sigma has no role in this computation. So we get this. So this is reverse channel. Okay. So you plan to catch 5 o'clock or 6 o'clock? Yeah. Huh? Okay, I will. Okay, isometric this. There are 2 more important channels. One is called, we have already seen that, but in this language, we have to write and compute the cross operator and other things. One is called, you have a question? Why we are putting? Otherwise, how will you get an operator? This is just a number. You need something. Yeah, you need something. So you kind of append it, kind of thing. That's all. Okay. Okay. Next thing is to talk about there's something called classical quantum channel. It takes a classical state to quantum, okay, which we have already, which is new. Quantum to classical is just measurement. We have already seen. We have seen it in detail, but we will do it again. So these are the two things. And there is one more thing I forgot. Then we will do what are called entanglement breaking channels. Okay. I thought actually, I mean, thought of proving up to entanglement breaking channel, but there is no time. I'm also getting tired. So I think I will stop here. So we will meet on Thursday after your talk.